Carrying on with permutations, the next case to consider. So case 3, we've got n objects, we are going to use them all, but they're not all different. Some of them are in fact the same thing. How does this change how we approach the problem? So let's narrow it down to, I guess, the simplest case. We've got 2 objects. If they were all different, then we can see very clearly there's 2 ways of arranging them. Or we would have said 2 factorial ways, which of course is the same as 2. But what happens if they're all the same? Well, now there's only one way of arranging them. So the question becomes, how did I get from 2 to 1? Now, a bit hard to investigate that with 2 objects, so let's have a look at 3. If there was 3 and they're all different, so there we go. 6, or we would have said 3 factorial. If 2 of those are the same, what's going to happen? There's our possibilities, 3. So we've gone from 6 to 3. Remember when there was 2 objects, we went from 2 to 1. So what mathematical operation have we done that was the same in both, I guess, is our question. Now, of course, if 3 are the same, now that one's down to 1. How did we get from 6 to 1? Let's look at 4 objects. 4 objects. Whoa, quite a few. So 4 factorial, 24. If 2 of them are the same to start off with, we end up with 12. So again, there's the question. How do we go from 24 to 12? The same operation that got us from 2 to 1, that got us from 6 to 3. Now the pattern's emerging. In both cases, we have divided by 2. 3 objects the same. We now have 4. So remember, we went from 6 to 1. In this case, we've gone from 24 to 4. What's the mathematical operation they have in common? We've divided by, but more importantly, it's not that we've divided by 6 or divided by 2. What we've divided by is 3 factorial and 2 factorial. And if 4 are the same, we've gone from 24 to 1. So basically, if we've got n objects, okay, we're going to arrange them, but x of them are the same, then the number of ways we can arrange them will be n factorial over x factorial. So n factorial, the number of ways we could arrange the n objects, but we divide by the number of ways we could have arranged the like objects if they were different. So 2 objects the same, well, if they were different, we would have arranged them 2 factorial ways, so we'll divide by that. So I guess what we're doing is we're dividing out all of those possibilities, because as far as we're concerned, they're now the same thing. How many different words can be formed using all the letters in the word Norton? Surname of a student I taught many years ago now, but I've been using this as an example ever since. Well, there's 11 letters in Norton, but there are 2 O's, so we'll divide by 2 factorial, and there are 3 N's, so we'll also divide by 3 factorial. And we end up with quite a lot of different words. We're not going to try and find them. Here's an HSC one. The letters A, E, I, O, and U are vowels, just in case. Can't assume anything. How many arrangements of the letters in the words algebraic are possible? So we start off with algebraic. There are 9 letters in algebraic. There are 2 A's. So 9 factorial divided by 2 factorial, we get 181,440. Why did they give that definition about vowels? Part 2. How many arrangements of the letters in the words algebraic are possible if the vowels must occupy the 2nd, the 3rd, the 5th, and the 8th positions? Look after your restrictions first. So the first thing we're going to do is place the vowels. There are 4 vowels, so 4 factorial, but there are 2 A's divided by 2 factorial. We now slot them into those positions. The next thing we have to do is arrange the, they didn't give us that definition, did they? The consonants. And there's 5 of them, they're all different, so 5 factorial, giving us a total of 1,440 possible arrangements. Voila, just a quick bit of theory today. So we'll add those to our list of questions to look at.